Hey guys, in this video we're going to go over an example problem with titration calculations. And so if you refer to your practice, you have number 1 here. It says calculate the pH during a titration of 30 milliliters of 0.5 molar acetic acid. It gives you a Ka with 0.5 molar NaOH after the addition of. And so we're going to calculate the pH using different volumes of NaOH that we're adding. Now, in order to be able to do this, we have to understand everything from the beginning conceptually. And then I also gave you guys the assignment to do the mind map because this can help you reference what's happening along the curve as well. So keep this out while we're doing this, these calculations, and you can use it as a reference. So here's what we have to do at the very beginning. We have to identify what species is the analyte and what species is the titrant. So we're looking for a couple of words. We're looking for of and with. If this says a titration of, then whatever comes after that is the analyte. Whatever comes after the word with is going to be your titrant. So for instance, if they said we titrate a solution of ammonia with hydrochloric acid, that means ammonia is your analyte, hydrochloric acid is going to be your titrant. So we're looking for those kind of terms to figure out who's the analyte and who's the titrant. So now that we know who's the analyte and titrant, we need to kind of figure out what kind of reaction is going to be taking place. So we have acetic acid, HC2, H3O2, and we're going to write its reaction with NaOH. You guys should be good at this by now. This is a double displacement reaction, so we're going to have water form, H2O, plus sodium acetate. Now, as we are writing this reaction, it's very important for us to identify what every little species is that is present there in the reaction. Well, acetic acid, we should know by now and identify that as a weak acid. Sodium hydroxide, we should be able to identify that as a strong base. Water is just water, we don't care about it because it's neutral. And NaC2H3O2, that is your basic salt. Now, how do I know it's a basic salt? Well, quite frankly, go back to your salts lesson. This is an ionic compound. It came from a strong base. It came from a weak acid to produce that. And so as a result, the Kb of this is going to be bigger than the Ka of that. And therefore, we will have a basic salt. Remember, also, we apply the very introductory stuff we learned about learning who is the conjugate acid and conjugate base. This got rid of an H+. So as a result, it turns into our conjugate base. This species here, the base, accepted an H+. So when it accepted the H+, it turned into water, which is the conjugate acid. So we have a couple of different things happening here. We're going to be working with weak acids, we're going to be working with strong bases, we're going to be working with basic salts, and if we have a mixture of the weak acid, basic salt, we're going to be working with buffers. So that will be happening along the way. Now the next thing that we need to know and do is find our reference point. Now what is a reference point? What do I mean by that? I need to know where the equivalence point is at. So how do I find that? Well, I'm going to find my equivalence point volume by calculating the moles of my analyte, doing a mole-to-mole ratio, and then using the moles of NaOH and the molarity of NaOH to solve how much volume has been added. Why am I working with NaOH? Well, here's your answer. You have a pH curve. pH, volume of titrant added, What is our titrant? It is NaOH added. So we know that since this is a weak acid and strong base, that our curve should look something like this. We've done enough now to be able to do this. What we don't know about this curve is where this equivalence point is at. We have to know this volume at the equivalence point in order to be able to relate this volume to these volumes here. So here is what we do. Molarity times volume, 0.5 molar. Volume has to be in liters. That gives us 0.015 moles of acetic acid. Now we're going to do a mole to mole ratio because we've got to get into NaOH. So 0.015 moles of acetic acid, 1 mole of acetic acid is equal to 1 mole of NaOH. So we also get 0.015 moles of NaOH. Okay, now we need to plug in the molarity of NaOH, which I pulled from the problem here, to solve for that volume in liters. And then we can convert it to milliliters. So when you solve for this volume here, you get 0.03 liters, which is equivalent to 30 milliliters. Now, what does that mean? That means on this curve, we have 30 milliliters for my equivalence point. If I know my equivalence point volume, I can always figure out my midpoint volume as well. If this is at 30 milliliters, my midpoint is halfway in between that, so that will be at 15 milliliters. And I can kind of use this as a reference, that's why I call it a reference point, to help gauge of where I'm at for each of these species that we're working out here. So let's do some other basic kind of titration stuff. Let's talk about what is happening along this curve. All right, so at the very beginning of the curve, you have weak acid only that is present there. As you are titrating, this concentration is decreasing because I'm putting more of this in there to react, and this concentration is increasing. So initially I had just weak acid only, but now I'm starting to make conjugate base even though I still have more weak acid than conjugate base. At midpoint, my weak acid is equal to my conjugate base, and after midpoint, my weak acid is less than the conjugate base. All in this region, however, we have a buffer. Now what happens when that buffer is depleted and it goes away? We have reached our equivalence point, and at our equivalence point we have just this conjugate base present only. And then what happens if I go beyond the equivalence point? I still have my conjugate base floating around in there, but now I will have excess sodium hydroxide floating around there. So knowing my ratios along the curve will also help me be able to approach this problem. So now let's look at each individual piece and kind of gauge from this reference point what I will be doing to find the pH for every single one of those scenarios. So for the first one, I'm adding 0 milliliters of NaOH. So I'm adding 0 of this here. Well, what do I have present there? I have just weak acid present at 0 milliliters of NaOH. So since I only have weak acid present there, what do you think my approach is going to be to find its pH? We are going to do the pH of a weak acid approach, which we all know how to do. We did that in week 2. Let's look at scenario B. We're adding 10 milliliters. So that's before we've reached our midpoint. So that's in this region here. So B will be in this area. What do we have present? We have weak acid and we have conjugate base present. What does that mean? It means we have a buffer. So what is our approach? Our approach is pH of a buffer, and that's something we learned in that week 2, how to find the pH of a buffer. Let's look at scenario C. We're adding 20 milliliters of NaOH. So that's beyond 15, we've gone past the midpoint. We're somewhere in this region. We haven't yet created or gotten to our equivalence point yet. So scenario C will be somewhere in this region. Well, what do I have present? I have weak acid and conjugate base still. Just my conjugate base is bigger than my weak acid now. Since we have both of these present here, we're still in the land of buffers. So how do we find the pH? We are going to use the pH of buffer approach. Now let's look at scenario D. Scenario D, we've added 30 milliliters. Where are we at on the curve? The equivalence point. What do we have present on the at the equivalence point? Conjugate base. What is a conjugate base? It's just a basic salt. So what is my approach for finding the pH at 30 milliliters? It's going to be finding the pH of a basic salt. Let's look at 40 milliliters. 40 milliliters is beyond the equivalence point. So for scenario E, we're in this region. What do we have here? What is present according to this curve? We have conjugate base, which is a basic salt, but more importantly, we have excess NaOHs. So what do we need to do? How are we going to find the pH of these put together? This conjugate base means nothing compared to this OH minus. So the OH minus is going to dictate the pH at that particular point. So in order to find the pH here, we're going to take the pH of a strong base approach. And again, these are just the same approaches, nothing fancy, that we did at the beginning of this unit before we started titrations. So now that we have created a reference point, you have to do this before you can get to here, or else you have no clue what you're working with. We have a reference point, we have an idea of what's happening. Now we can carry out our game plan and answer the question, what is the pH at each one of these instances? So I'm going to kind of erase all this. I don't want to leave it. And let's start our calculation for A. So remember what we have at scenario A. We have just weak acid that is present there. And you can, if you want to, use your little sheet, mind map, if you need help with this as well. You can look along with that and work the problems out with us. So if we have just weak acid, I am going to first have to write my reaction. It's not going to be the reaction with NaOH because I've added 0 NaOH. So it's not reacting with that. It's just floating around in water. So my reaction that I'm writing is the acetic acid plus water. Now, that reaction is at equilibrium. We've created H3O plus C2H3O2 minus. Now, this doesn't matter. We plug in our initial concentration, minus X, 0 plus X, 0 plus X, 0.5 minus X, X, and X. So what am I doing here? I am taking our acetic acid, which is by itself, because 0 milliliters of that NaOH has been added, and I am using the pH of a weak acid approach. We write our reaction with water, we complete our Rice chart, we need a K expression. Ka is equal to H3O plus C2H3O2 minus over 8C2H3O2. Now we get to plug in our numbers. So 1.8 times 10 to the negative fifth is equal to x squared over 0.5 minus x. We get to neglect this x, and we solve for x. X in this case, remember what it's equal to? It's equal to the H3O plus. Why are we wanting to know that? It's because we want to plug it into our pH formula. Right there, we want to find our pH. So X is equal to H3O plus, which is 0.003 molar. So then we take the negative log of 0.003, and that pH is equal to 2.52. So this is my starting pH. I'm going to sketch that curve again here on the side. Let me do that in orange, so we can see what's happening as we go along the curve. So pH was here, volume of NaOH is here. We said 30 was our reference point of where the titration spikes. Initially, we're saying that we have at part A a pH of 2.52. So we have just weak acid there. That's fine. Acetic acid has a pretty large K value, so it can be considered a little bit stronger than most. And so that is an acceptable answer. So the answer for A, the pH, if we've added 0 milliliters of NaOH, is 2.52. So all we do, we analyze what's there, and we use the proper approach according to what's present. Now let's look at scenario B. Now scenario B, we now have added some NaOH. So my reaction is no longer just acetic acid by itself. I now have mixed these two things together, so I'm going to write that reaction together again. That's what I wrote at the very beginning. So here we go, we have HC2H3O2 plus NaOH. That's going to form H2O plus NaC2H3O2. Now, we told ourselves, based upon where we're at on the titration curve, that we should have a buffer present here. When we do our calculations and fill out a rice chart, we will figure out that, yeah, we do have a buffer, because we will end up getting some amount of this weak acid and some amount of this, your conjugate base, aka basic salt, floating around in that solution. And whenever that's the case, we have a buffer. So before I start just plugging in numbers, I have to realize that I'm basically taking this NaOH that has a molarity and a volume of its own individually, and I am mixing that with the acetic acid, which also has a molarity and a volume on its own. Remember, I always tell you this in class, if I have something with a molarity and volume, and I'm mixing it with something else with a molarity and volume, I always have to do that famous equation, M1V1 equals M2V2. And I have to do this equation in order to figure out what is the molarity once these two are mixed. So I'm going to do that off to the side here. We're going to start with acetic acid. M1V1 equals M2V2. And we also have to do it for the NaOH, because once it mixes with that acetic acid, it's going to change its molarity too. Both of these are going to have new concentrations once they're mixed. Now, for acetic acid, M1 is what I started out with, 0.5. V1 is what I started out with, 30. M2 is what I'm solving for, and V2 is my new volume. Now, how do I figure that out? Well, originally, I had 30 milliliters of this floating around, and then I've added 10 milliliters of NaOH to that. So my total volume here is going to be 40 milliliters. So that's what I'm plugging in for V2. When I work that math there, I get my new concentration of the acetic acid to be 0.375. And this is what I can plug into my rice chart. So 0.375 molar. I have to do the same thing with NaOH. So I started with 0.5 molar NaOH. My volume that I started out with, how much did I put in there? 10 milliliters. So 10 is my initial volume. M2 is what I'm solving for. And what is my new volume? It's these volumes added together. So that is equal to 40. So when I solve for this new molarity, I get 0.125 molar. And that is what I plug in right here. Now, I originally don't have any of that sodium acetate just floating around in there. I'm going to end up making it when these two mix. Now, how do I figure out the rest of this rice chart? Well, it is just a limiting reactant problem. This is my limiting reactant comparatively. So I subtract according to a mole to mole to mole ratio. Because they're all 1 to 1 to 1, that's why we're adding and subtracting 0.125 across the board. So now what do I have left over? What has happened? All of this sodium hydroxide that has been added has been neutralized. You've decreased your acetic acid concentration to, now it is 0.25 molar. And you've created some basic salt here, and you have created 0.125 molar of that. Now, because I have both this guy and this guy floating around in that solution, that is why this is a buffer. That is why the whole idea of right here, that is your buffer equation, because if you were to work a rice chart for any area along this part of the curve, you will notice that you will have both weak acid and conjugate base, or aka basic salt, present there. And that's where we have a buffer. Now remember how I said that 10 milliliters was before the midpoint, right? Because this is before the midpoint, we said that our weak acid should be greater than our conjugate base there. Is that true? Or do we just memorize that for the heck of it? No, this is true. Mathematically, we have proven that our weak acid is greater than our conjugate base, aka basic salt, because we are at a volume before the midpoint. Now, what do we do from here? We're trying to find the pH. We use our buffer equation. So remember, you only use this equation if you have a buffer. You better not use it for anything else. Base over acid. This is the base because it's my basic salt, conjugate base. This is my acid. So I'm going to plug in my pKa. Where do I find that? I take the negative log of my Ka value. That ends up being 4.74 plus log base is 0.125 and acid is 0.25. So now I plug all of this information in and I get a pH to be 4.44. I asked myself, does this kind of make sense? Well, I started at 2.5, now I'm only at 4.4. My pH hasn't spiked up or down, and so yes, this is an acceptable answer according to the scenario for this titration that we have. So this is how we approach and work out in our final answer for scenario B. Now we're going to do the same thing for scenario C. In this instance, we've not added 10 milliliters, but we've added 20 milliliters. Now this is not adding volumes on top of each other. We're assuming that they're all starting from 0, okay? So it's not like 20 plus 10. We're just starting from 0. So 20 total has been added to this scenario. So we're supposed to still be in the buffer region here. Let's double check that. What do? We keep our reaction. We find our new molarities because we're mixing volumes. We will now have different values in our rice chart. So let's see here, and I think that's good. All right, so let's find our new molarities first. M1.5, V130, again, we're using the initial amounts just like we did before. Our new volume is now 30 plus 20 because we started with 30 of this guy. We added 20 from the other guy. And so V2 is equal to 50. That ends up giving you a value of 0.3 molar. And we're going to plug that in right here. We're going to do the same thing for NaOH. So that was 0.5. 20 is its initial volume before mixing. Mixing, that volume is 50. And then we solve for that, it ends up being 0.2. So 0.2 is your value here. We're still assuming that we're starting from 0, right? We're starting from 0, we're just asking ourselves, how much will we have once these react from the very beginning of the titration? This guy is still my limiting reactant. So subtract 0.2, subtract 0.2, add 0.2. I still have 0 left over. That's good. We've neutralized my strong base here. I have 0.1 left over. I have 0.2 produced here. Do I still have a buffer? The answer is yes. I still have a buffer because I still have a value of that and I still have a value of that. So now what do? I am going to plug these new values into my buffer equation. 0.2 goes here, 0.1 goes here, and calculate my pH. In this scenario, you should get a pH of equal to 5.04. Now, let's ask ourselves, remember how we said after the midpoint, your weak acid is supposed to be less than your conjugate base, but you still have a buffer there. Is that scenario true? We're past the midpoint because the midpoint's at 15 because the equivalence point is at 30. Do we have more of our base than our acid in our buffer? The answer is yes. So that's why these ratios matter, is to conceptually understand what's happening along with the math. And they like to ask questions about that. So this is how we take the pH if we are any point along in that buffer region. So now let's move to scenario D. Scenario D, we conceptually said that, hey, we pretty much have a basic salt only on our hands. Well, how mathematically can we prove that? What do we do if we want to find the pH? We should no longer have a buffer there. So I should be able to erase that. Let's erase these values, and this has changed here as well. That's no longer there. All right, so let's start with scenario D. Now we have added 30 milliliters of the NaOH into here. So before we start plugging in numbers, we have to figure out the new molarities because we're mixing volumes. And so 0.5 times 30 equals M2 times 60. Where I'm getting 60 is those two volumes added together. So I end up getting a molarity of 0.25. So I'm going to plug in 0.25 here. Now let's do the same thing for the NaOH. 0.5, 30 coming from here equals M2 60 coming from added together. That also is 0.25 molar. Well, looky there. Remember when we were doing our titration lab, and I told you guys that what does equivalence point mean? It means that these two are equal. It means that they will fully react with one another to where we have nothing in excess. That is what equivalence point means. What will happen? How do I find the pH of that? Well, I'm going to be producing 0.25 molar of this salt. This salt is the only thing that is floating around in there. Well, how do I take the pH of a basic salt? We learned that in week 2. So that is our approach to find the pH here. We have completely neutralized both the analyte and the titrant, and now all we have floating around in there is our salt. So what do I need to do to find the pH of a salt? Well, I'm going to write this reaction with water, but if you notice, hopefully you notice this reaction with water is just the reverse reaction. Once you reach equivalence point, your reaction is just going in reverse. That's what equilibrium is about. We can go both ways. All right, so I'm going to rewrite this. NaC2H3O2 plus H2O goes to HC3 2H3O2 plus NaOH. Now, to better understand what's happening here, we can write this net ionically where we cross out Na as a spectator, and you see how I'm going to have little OHs, not a very large amount because it's just a little above 7, but we're going to have some little OHs kind of breaking apart in this scenario. And so we will have to use the approach of a basic salt to find the pH, which is basically just a weak base. That's what basic salts are, weak bases. So if you forgot how to take the pH of a weak base or a basic salt, go back and look at your notes on how to do that. What I'm going to do is start with this concentration that I found here. 0.25, water doesn't matter. This is 0, plus X, and minus X. Do you see how I'm using these amounts that I started with, or that I ended with in the right chart? And now the reaction is just going in reverse. So I have 0.25 minus X, X, and X. Since this is a basic salt, I need a Kb expression, which is OH minus times HC2H3O2 over C2H3O2 minus. And I need a Kb value. So how do I find a Kb value if I know a Ka value? I use Kw, which is Ka times Kb. So I'm going to use Kw, 1 times 10 to the negative 14th. I'm going to solve for Kb, and that ends up being, I think it's 5.56, yeah, 5.56 times 10 to the negative 10th equals x squared, 0.25 minus x. We still get to neglect that x. Now we solve for x. X is equal to your OH concentration in this case. Don't get lazy. It's equal to OH concentration because we used a Kb because there's OH there. Now, that is equal to, let's see my math here, 1.18 times 10 to the negative 5th. Can we find pH directly from OH? The answer is no. We have to find POH first. So POH is equal to negative log of this number, and that is equal to 4.93. Then we can find pH from this by taking 14 minus 4.93, and that gives us a pH reading of 9.07. We ask ourselves, does this make sense according to our curve? Well, at this equivalence point, that pH needs to be bigger than 7. And 9 is bigger than 7, so yes, that pH makes sense according to our curve. So this is our approach. if we have reached equivalence point. Now again, I would not be able to know that this is the equivalence point or this is what's happening if I didn't create and figure out what that reference point was at the beginning. I created my rice chart, I realized I only had a basic salt there, I used my basic salt approach to figure out my pH. So now we're going to work on scenario E. For scenario E, we have a new volume we're adding. So let me erase all of this stuff. Okay, I'm getting there. Almost. All right. Scenario E, I now have added 40 milliliters of my base. So again, I'm going to go straight into finding my new molarities before I plug into my rice chart. We're probably not going the opposite way anymore. Let's see what's going to happen. That's bothering me. There we go. All right. So M1 for HC2H3O2 is 0.5, V1 is 30. Again, I'm just using the initial stuff given to me every time. M2 is what I'm solving for. My new volume is 40 plus 30, so that's equal to 70. And so my new molarity here is 0.214. Let's plug that in. Let's do the same thing for NaOH. So 0.5. Initial volume, remember I'm pulling from here, into volume mixed is 70, and so that molarity ends up being 0.286, and that's what I'm plugging in here. So what do you notice is now happening? Well, before I've reached my equivalence point, NaOH was my limiting reactant. When I reached the equivalence point, they kind of both were the limiting reactant. Now that I've gone beyond the equivalence point, I've switched my limiting reactant. It's no longer NaOH, it's now the acetic acid. So he is the one that is going to dictate how much I have produced and consumed along the reaction. So I have none of this left over. Completely neutralized my analyte. I will have some amount of NaOH left over, which is equal to 0.072. And I have 0.214 molar of my conjugate base floating around in there. So do you see how we talked about at the beginning, at this part of the curve, you have conjugate base floating around and you have excess OH minuses. Now, which one of those will dictate my pH? A weak salt is nothing compared to a strong base. The strong base will supersede that pH. So we are going to use the approach, the pH of a strong base. To do that, how do we find the pH of a strong base? Well, this concentration is exactly equal to your OH minus concentration. But since it's a base, we have to find pOH first. So we take negative log of 0.072, and that is equal to 1.14. Then we can find the pH by taking 14 minus this, and that is equal to 12.86. We ask ourselves, does this make sense according to our curve? Well, we predicted that it will kind of end pretty high in like the 13-14 range. That's pretty darn close. So this is the approach, the scenario, and the answer to part E. Now, I know that this stuff is a lot, okay? But it is very important that you guys understand the big picture. You see how we're using stuff from at the very beginning of acid base, whether as like knowing conjugate acids and conjugate bases and identifying weak acids and things like that. We're using the stuff we learned in week 2, how to apply the pH of everything. We're learning our knowledge from week 3 of titration curves and equivalence point or references and stuff like that. And now Week 4, we're putting it all together in a big picture. If you guys can understand and be able to do this, then I have no doubt that you won't struggle with acid-base, okay? Do not make this harder than what it is. We write our reaction, we find our reference point. If you are in doubt, just do a rice chart. If you don't know what your reference point is, if I couldn't have done this at the very beginning, or if I didn't have time to do it, I could have done a rice chart, bypassing that, and figured out what I had present there. So therefore, how do I take the pH of that? So practice this, work hard. There might be some free response questions pulled from this type of scenario. Maybe it wouldn't be every single question here, but maybe they just asked question D out of the whole thing. All right, so that could be one part of a free response question. Don't think that all of your acid-base stuff is going to be on stuff like this. It can be very simple concepts there as well, okay? So we're going to be doing this. You're going to finish the rest of those calculations, and then we're going to be working some free response problems. So I hope this was helpful. I hope this video actually recorded, because my first one did not. See ya.